we don't finish it all today, that's okay, because we'll have some time to catch up a little bit. Oh, and for anybody's, I'm trying to think. Crystal's coming in today, but I think it's maybe 1 o'clock. If anybody's around, we're gonna trial a walker with her, a new walker with her. She's got a walker at home that I lent her that she's been using, but I think she's at a point where she can use a different style of walker. So I'm gonna actually go over to Advanced Medical, and they're gonna let me borrow one to show her that she's interested in trying out. So I'm gonna do that with her today. And Randy, who most of you haven't got a chance to see, because now he actually qualified for that study at the University of Cincinnati. We had tried to get him to where he could walk at least 3 minutes at 0.3 miles an hour on a treadmill for the baseline testing, and he was successful. And so they said, "Hey, we appreciate it. We're going to they're entering the study last week, and so we'll see. Well, hopefully, I want him to come back, and we'll show you. She's been taking videos along the way, so it'll be kind of interesting to see. I can show you when we first saw him a year ago to where he is after the study, and maybe some points along the way. We can maybe show that when we're doing our clinical neuro. And he may come in, and maybe we'll do some more stuff with him and higher functioning stuff, and continue to work with him in the clinical neuro and kind of keep following his progress. That'd be kind of fun. All right. This is stuff you already know. A lot of the stuff is somewhat review. So components of the midbrain. We've got the medulla, pons, and midbrain. I'm not sure why I went from bottom to top there, but medulla is down here, pons is here, midbrain is there. A little more close-up detail here. So in this case, this is one of the pictures that you will see, and this is on that in your neuro lab manual, that picture. And just to point out some things, this is the cerebral peduncles here. And then this is actually left on here. This is the optic tract, optic chiasm. The cut ends of the optic nerves here are shown there. This D sitting out here, this is actually your lateral geniculate nucleus that your optic tract is going to, the lateral geniculate nucleus sitting there. Your thalamus is actually sitting up here. They'd cut it away. The thalamus sits just above that, and that lateral geniculate nucleus is off that thalamus. This is your oculomotor nerve, one of them coming out there in that interpeduncular fossa right here. Here's our mammillary bodies. Basilar pons, basilar groove right there in the front where the basilar artery rests. We have this L right here. This is the tag end of the trigeminal nerve as it exits the pons. And then this is the abducens nerve, right? Cranial nerve number 6 that comes out. That's that most medial at this pontomedullary junction. So then you just kind of start working your way out, and then so 6, 7 out here. Here's 7 here, and this is 8 here. This vestibular cochlear, facial, 9 glossopharyngeal. I'm not sure where 10 is on here. Maybe 10 got taken off. Some of these not always. It's hard to get a brainstem out without tearing the cranial nerves because those are pretty embedded in there, so it's really hard to get that out. This is the spinal accessory nerve here coming down. It's going to come up and then up through your foramen magnum, back down, out to go to the SCM, upper traps. Oops. You can see some of the little tag ends of the hypoglossal nerve there that's coming out of this ventra-intermediate. This is the ventromedian fissure. There's a ventra-intermediate kind of sulcus, which you don't have to know that, but just that's where that hypoglossal nerves are coming out of. Got our pyramids right here. And then right in here is the decussation of the pyramids. The crossing point is right down in that region. Kind of see that right in here is where that starts. Thing it's hard to see because they're kind of hidden by the cranial nerves is the olives right here. So there's your olives. So those are most of the structures that you need to, pretty much all the structures you need to know from a anterior view, ventral view. Now from the posterior view, you could see either one of these pictures in the lab practical. So let's just talk about it. So this is the thalamus sitting back here, and that they left on top there. And this is your lateral geniculate nucleus is here. This is the medial geniculate nucleus or body right here, H. That's that relay for some hearing, reflexive hearing information. So this is your tectum, your corpa quadrigemina which is made up of your four bodies, which is your two superior colliculi and two inferior colliculi. Okay. The superior colliculi, if you remember, those are for relays for reflexive visual kind of connections with the MLF, so you look to something, and then the inferior colliculi are for hearing, that subserve that same thing. When an auditory information comes in, that reflexive orientation of the head to that, some of that hearing information gets to the medial geniculate nucleus via this. This is called the brachium of the inferior colliculus. Brachium is arm, so there's just a few fibers that go this way, so they go to conscious awareness of hearing there through that brachium of the inferior colliculus. And then moving down more into the pons area, and then we look at the cerebellar peduncles, so it attaches the cerebellum to the back of the brainstem. There's our middle cerebellar peduncle, that big one there. This would be the superior cerebellar peduncle right here. And they show it extending all the way up into here, kind of like that. This superior cerebellar peduncle. Then this would be the inferior cerebellar peduncles, this region right here. On this specimen, middle, superior, and inferior there. Middle, superior. And it all just depends on how you use your scalpel to make those cuts to how that looks. But you should be able to kind of generally know by seeing any of those two versions which one of those I would highlight on a practical exam. This right here, this space back here, that's the rhomboid fossa, which is the floor of your fourth ventricle. Okay. Then down here we have, this is the center line of our medulla here. Then we have our gracile tubercle and cuneate tubercles here. Those are those bumps here, gracile and cuneate tubercles right here, which lies just deep to that is the gracile and cuneate nuclei. And then we have this Y is the fasciculus cuneatus, upper extremity, proprioception, and X is the fasciculus gracilis, lower extremity, proprioceptive information. Okay, that's pretty much covers that. Here we go. Here, one thing out here. This is what nerve comes off the back? The only cranial nerve that comes off the back is the trochlear. Just going to your superior oblique muscle, SO4, superior oblique. And remember this, the nucleus for it sits on this side. It crosses over before it comes out the other side. And here it crosses over like that before it comes out the back. Deep inside of there, of course, is where those nuclei are sitting. So we have, within the brainstem, kind of like the spinal cord, we have vertical tracts that run through the brainstem. We have sensory pathways, we have motor pathways, we have autonomic pathways, which you know all of these already. Some of these tracks run right through the brainstem, just like a conduit, don't make a lot of connections or stops along the way. Things like the spinal thalamic tract, pain and temperature from your body. It goes up through the brainstem. And then the medial lemniscus, proprioception from your body going up through the brainstem. The sympathetic pathway from the hypothalamus, dorsal longitudinal fasciculus, the DLF, is this fibers that run from the hypothalamus down through the brainstem and into your spinal cord to go to the preganglionic sympathetic neurons at your spinal cord level in that thoracolumbar area. Okay. And then also that DLF also projects all the way down to your sacrum as well to interact with the parasympathetic preganglionic neurons in the S2 to S4 region, okay, in the sacral division. And then cortical spinal tract fibers that go from your cortex down to your spinal cord, they go through the brainstem as well. So those go through with relatively unaltered. But some do have synapses within the brainstem. Some pathways make connections in the brainstem. Specifically, the spinocerebellar pathway stops in the brainstem, essentially. It stops in the cerebellum, which is off the back of your brainstem. The cortical bulbar tract fibers, those are the ones that go from your cortex that run with the cortical spinal tract, but they stop when they interact with motor cranial nerves, okay, for your motor cranial nerve function, voluntary motor cranial nerve function, cortical bulbar tracts. Corticopontine fibers, so the corticopontine fibers, they're also running with your cortical spinal, cortical bulbar fibers, but they stop and synapse in the pons and deliver a copy of your motor messages to the opposite side of the cerebellum. Those are the corticopontine fiber pathways. And then cortical reticular fibers. These are fibers that go from your cortex down to your reticular formation, reticular system within your brainstem that drive some automatic postural gross movements, but also influence descending pain pathways and those kind of things. So those are some that have those things. And then we have vertical tracts that actually originate in the brainstem, okay? And mostly we're talking medial activating system pathways, posture and gross movement, motor pathways, tecto, rubro, reticulo, vestibulo, although rubro is not really, rubro is kind of gross motor, but it's more just flexion of the upper extremity, as we remember. Vestibulospinal, and then the cerebellar and raphe spinal tracts, those are the ones that tend to do more of the descending pain control, the cerebellar and raphe spinal. Those also have influence over general activity level of the motor system. Remember, they play a role in, like, if you get tensed up when you're nervous and those kind of things. The cerebellar and raphe spinal tracts can also influence motor a little bit as well, in addition to their role in descending pain control. So this is just showing you those. Remember we said there's, in the back of the brainstem, this is where we tend to see the sensory pathways that move through that brainstem relatively unaltered. So this is the the medial lemniscus dorsal columns, the medial lemniscal system coming up. It's the medial lemniscus once it's up in the brainstem, and the spinal lemniscus when it's in the brainstem. It's called the spinal lemniscus, right? And so those two pathways go up the back of the brainstem relatively unaltered. And then coming down the front of your brainstem is mainly motor pathways. Some of those pass all the way through the cortical spinal tract, relatively unaltered, but other ones stop. The cortical bulbar and cortical pontine fibers branch off of that and stop in the brainstem. So that's what we're just showing you there. Just an appreciation for sensory towards the back. And here's the spinal cerebellar tracts coming into the cerebellum, which is a sensory unconscious sensation pathway that come up the back of the brainstem. And then, all this middle area of the brainstem, this is what we're going to be talking a lot about today, is this tegmentum region, which within the tegmentum is this reticular formation, which has got some divisions to it and nuclei associated with it. So the tracts are kind of running in the front and back of the brainstem. The middle is preserved for a lot of integrative function, and where some of these other things happen in the middle of the brainstem. So if we look at some of the longitudinal sections in a sagittal cut right here, we have the basilar section, which is the front part. of the brainstem, and sometimes people extend it all the way up in here. So the basilar pons, the basilar section, primarily motor, cortical bulbar, spinal, pontine, and reticular tracts that originate there or pass through there. And then we have the tegmentum, which is all this kind of meaty center right here, which is more sensory tracts tend to run that back part of the tegmentum. Cranial nerve nuclei are in there, the medial longitudinal fasciculus, the reticular formation is in the tegmentum, and then the tectum is the roof, which is only in the midbrain. We have the tectum right here, which is that superior and inferior colliculus. So those are the longitudinal sections in a sagittal cut. So let's go into the reticular formation now and just talk about this. It is a complex neural network in the tegmentum. Lots of interneurons, a fair number of nuclei that are in there, and then so we'll talk about those. We can talk about the reticular formation also in 3 longitudinal zones. But these 3 longitudinal zones, we're going to be appreciating it from a coronal or anterior-posterior direction here, okay? So here's looking at the back of the brainstem, and they've got kind of these dashed lines to separate it into these zones. And so we have this, midline zone here, and then we have the medial zone here, and then this lateral zone out here. Okay, so we have a midline, medial, and lateral longitudinal zones. And then they point out these are some nuclei that are in those zones. These happen to be mainly in the lateral reticular zone. This is the ventral tegmental area, the VTA, the pedunculopontine nucleus, the locus coeruleus are in there. But we'll go into each of these longitudinal zones now and talk about their main role, what's in them. Okay, so lateral zone. The lateral zone is like an integrative function. It integrates sensory and cortical input. So some integration. So some sensory information goes into that lateral zone. So remember some of those slow pain pathways. The slow pain. Some of those spino-mesencephalic tract and that kind of stuff, they may stop in this lateral zone to deliver some pain information. And then you also have some descending cortical pathways that go into this zone too to help regulate your control over some of those pathways. So if you're getting pain coming up into that lateral zone from one of these slow pain pathways, you can have your cortex also go down and make some sense of that pain and help to enhance the descending influence of the descending pain pathways through cortical influence or not, and that's where you get some of this chronic pain from. It's a lack of your ability to use your cortex to help maintain that appropriate balance between these integrative areas to maintain appropriate levels of control of pain. That information, once it comes into that lateral zone, can then be conveyed to the medial and midline zones. And then those project to the cerebrum, cerebellum, spinal cord, so we have projections going all different directions out of these zones. The lateral zones also plays a role in just adjusting general level of neuronal activity and arousal. Okay, so you have what's called the reticular activating system, so it's in the reticular formation, and the reticular activating system, part of it is also in this lateral zone. Okay. Then we have the medial zone, which is where some of our vital function centers are in that medial zone. Our respiratory and cardiac centers are in the pons and medulla, are located in the medial zone of this reticular formation area. And then also they project to cranial nerve nuclei and the spinal cord to help drive some of those functions. And then also the reticulospinal tracts are the posture, gross movement reticulospinal tracts. We have the medial and lateral reticulospinal tracts. Those are in the medial zone where they start. Okay, and then we have the midline zone. This is where we have descending pain pathways via the raphe nuclei. The raphe spinal tracts, those originate in that midline zone and project down to the dorsal horns of the spinal cord and help regulate pain. Midline zone also plays a role in adjusting levels of consciousness, okay, just how aware and conscious you are via projections up to the cerebrum to deliver neurotransmitters to help regulate that. So that was looking at the different longitudinal zones and what happens in each of those zones. Now we're going to talk specifically about some distinct nuclei that happen to be in some of those zones, and also the neurotransmitters they use to exert their influence. Okay, so these are the reticular nuclei. We have the VTA, the ventral tegmental area. Okay, and that's an area in the midbrain where your substantia nigra lies, but there's another area just in front of that substantia nigra called the ventral tegmental area. And so you're seeing in the midbrain, we do have a couple really important areas where some cell bodies lie that project up to the cerebrum for helping control a lot of things, including movement with the projections to the substantia nigra up to the basal ganglia. But we have this VTA, the ventral tegmental area, that projects up to the kind of prefrontal cortex, limbic system area is where it does most of its projections, some to the hippocampus here in the medial temporal lobes. It secretes dopamine, just like the substantia nigra does, but substantia nigra is going into the basal ganglia circuitry. This is going into cerebral circuitry outside of the basal ganglia. It helps provide things like for motivation and decision making. When you have appropriate levels of dopamine, you feel motivated and you hopefully make good decisions and those kind of things and logical decisions. There's also pleasure with that when you have a amount of dopamine. So amphetamines and cocaine stimulate this area, and that's what part of that high is from, a little excess dopamine being squirted into those prefrontal cortices and limbic areas and so forth. Morphine inhibits inhibitory input to this area. So, if you inhibit an inhibitory input, you stimulate that. So morphine ends up stimulating this VTA, and again, that's why people can sometimes get high from morphine. It also helps with some pain control too, obviously. Morphine also binds to some peripheral receptors too that can help. But if you have excessive activity of this, has been associated with schizophrenia. When you have unregulated VTA activity, certain antipsychotic medications or block D2 dopamine receptors. So in this prefrontal cortices and limbic areas, you have some D2 dopamine receptors that bind to that. And if you have schizophrenia and you're in psychosis, you don't want so much dopamine. You want to block some of that dopamine binding to those receptors. So some of the antipsychotics block D2 receptors. And so if you block, remember D2 receptors are also how the indirect pathway exerts its influence and keeps you downregulated and inhibits movement. So if you block D2 receptors, some of those you also block in the basal ganglia. So if you're blocking the indirect pathway, you get too much movement. So people on long-term antipsychotic medications often get dyskinesias because they start moving too much because they have too much influence of the direct pathway because they're getting their indirect pathway slightly blocked in the basal ganglia, in addition to trying to block these dopamine receptors in the prefrontal cortex to help them with their psychosis. That would be a tardive dyskinesia. Tardive is something medication related, so it's common for people who are schizophrenic, who are on long-term antipsychotics. You'll notice that they have some of these dyskinesias and so forth. So yeah, it's a tardive dyskinesia. You've heard the pedunculopontine nucleus a few times. Pedunculopontine, it's right at that junction between the pons and the cerebral peduncles, right at the junction between, this is the cerebral peduncles right here, and here's the pons, the junction between the pons and the midbrain right there. That's the pedunculopontine nucleus. We have talked about it mainly for the role it plays in helping with posture, gross movement, and gait. This is a brainstem center that does influence movement and kind of can stimulate induced walking. If you just stimulate the pedunculopontine nucleus in a cat, it will walk via that stimulation. That response is not as, they can't do this in humans, but we do know that it plays some role in automatic movements for walking and so forth, but it's probably not as strong as you do see in like four-limb animals and so forth. We have a little more cerebral control. The pedunculopontine nucleus can drive a lot of four-limbed animals' walking movements because you get to balance on four limbs. It's easier than trying to balance on two limbs and so forth. You can be a little more automatic in nature than even human walking can be. But it exerts its neurotransmitter it uses is acetylcholine. Okay, it has connections with the globus pallidus, the subthalamic nucleus, the basal ganglia. Those are the output nuclei that project to the pedunculopontine nucleus to help maintain normal tone in our postural muscles and influence those vestibular and reticulospinal tracts. And we lose some balance there in Parkinson's disease. We get too much tone, both in agonist and antagonist, so the pedunculopontine nucleus gets a little overactive and causes you just to kind of stiffen up in general and get rigidity. Then the raphe nuclei, these are serotonin-producing neurons, and they are in the midline zone primarily. They can project up to the cerebrum. Okay, so the raphe nuclei they're in the midline zone and they're distributed. Some are down here in this pons medullary junction, and some are up here towards the top of the pons, towards the midbrain. They can project throughout the cerebrum. So you see they have really diffuse projections and deliver serotonin to the cerebrum. But they also have descending tracts, mainly from these lower raphe nuclei that project down to the spinal cord for pain control and deliver serotonin at the dorsal horn. Okay. They may play a role in the onset of sleep and your quality of sleep. They have a profound effect on mood. Prozac prevents the reuptake of serotonin, so that your system stays in the synaptic cleft longer when you have Prozac on board. It provides general modulation of sensory, motor, and autonomic nervous systems. So these serotonin levels will just help to modulate overall sensory experiences, motor and autonomic system, and then plays a role in descending pain control, at least the medullary portion of that, this down here. So it does quite a bit, a lot of stuff happening with that. And then we have the locus coeruleus. The locus coeruleus here, right here, and then also what's called the medial reticular zone nuclei. I don't know how they're all fitting in there, but they just keep putting more stuff in there. These produce norepinephrine, and you guys have seen this picture before. We've talked about it before when we talked about some of these diffuse projections up into the cerebrum. They project throughout the brain and spinal cord. These are most active when you need to be alert. This is part of your reticular activating system, the RAS, reticular activating system. When you're alert and awake and upright, these tend to be more active to keep you alert and awake and upright. The medial reticular zone also does play a role in regulating the autonomic nervous system, and also some role in inhibition of pain. So some of these have some diverse roles. The cranial nerve nuclei of the brainstem, you've seen all these. This is what we just got done going through. We are going to now be doing cross sections through the brainstem coming up, and you'll start to see these in the cross sections. So that's all I wanted to show you there. Are you ready? Go through the regional anatomy and the cross sections. Not too bad. You only need to know a few pictures. So we're going to start with the medulla. We're going to work our way up the brainstem. Okay. So good again, no big picture here. Functions of medulla. What are the main things the medulla is from a functional standpoint that is important to us mainly as physical therapists? Is there is some contributions to the control of eye and head movements. Okay. Some of those reticulo-vestibulospinal tracts that start there and help coordinate with eye and head movements, and also the vestibular nuclei are right at the top of the medulla there. They help, there's coordination of swallowing, okay, so glossopharyngeal nerve and so forth, and the vagus nerve are coming out around that medulla and are in the medulla and the nuclei for those. Regulation of cardiovascular, respiratory, those your respiratory and cardiac centers are in the medulla, and visceral activity. So the vagus nerve is coming out of there, regulating a lot of this. So those are some of the big things we care about as the function of the medulla, okay. So we're going to go through the internal anatomy of the medulla in the different couple cross sections here. So we're going to start low. We're going to start, so this is the approximate location of the first cross section you're going to see. So this is the cross section through the low medulla at the decussation of the pyramids. This is what we're looking through, the cross section of the decussation of the pyramids. So essentially, I'll put this on one piece of paper for you for the entire external and internal, but these are the structures you need to know in this picture right here. So when you're going through and studying these pictures, those are the structures you would need, or you are responsible for in the lab practical, okay? Or for the quiz on Friday. So the quiz on Friday will be one of these cross sections. And it'll actually, I'm just going to put up a picture. It'll be one of these pictures. It'll be a little bigger than that, and it'll just have on your quiz form, it'll actually have the name of the structure, and then you just have to write the letter that matches up with that name of the structures. You don't have to actually write the name of the structure in. For the lab practical, you have to write it from memory. This will just be you saying, it'll just have the name of the structure, and you just have to write which letter next to it. This will be five of those, 5 questions on one cross section. So, all right, so let's go through these. We're looking at nucleus gracilis is the first thing on here, and it's just starting to, you're just starting to see it here. We're actually not quite in the meat of the nucleus gracilis here. That's the lighter color. So remember the nuclei, cell bodies are going to be lighter on these stains, and white matter is going to be darker. Okay, tracks and pathways and are going to be darker colored. Okay, so that's the nucleus gracilis, and then this is the fasciculus gracilis. Is this area kind of around it here? Here's the fasciculus gracilis here. It's the pathway coming up. That's coming up. That's bringing those axons that are going to eventually synapse in the nucleus gracilis. Okay. And then we have the fasciculus cuneatus, which is D right here. We don't see the nucleus cuneatus yet. It's a little higher up. We're just seeing a little very bottom tip of the nucleus gracilis here. I wouldn't even probably, it's not the greatest cross, but you should know what that little area is there. All right, and then we have E, the spinal tract and spinal nucleus of cranial nerve number 5. So E out here, this little darker area right here, that's the spinal tract, and this is the spinal nucleus right here. So the spinal tract of cranial nerve number 5 is, so remember, these are fibers that come in the pons, right? For cranial nerve number 5, they come in via the pons, and they descend, and they start making their connections as they're descending down. And this little area that they're descending down is called the spinal tract of cranial nerve number 5. And then they're synapsing with the nucleus that is right here that projects all the way. Remember, this nucleus is really long. This is that pain and temperature from the face. It projects all the way from the pons down through the medulla and into the spinal cord. It's called the spinal nucleus of cranial nerve number 5. But right along the edge of it, as these axons come down and then make their connections, that forms a little tract called the spinal tract of cranial nerve number 5. So that's what you're seeing there, is the spinal tract of cranial nerve number 5. Then G is the posterior spinocerebellar tract. And H is the anterior spinocerebellar tract. And you really don't see a nice distinction there, like edges of it. You just kind of have to know regionally where that would be, okay? You just have to know, if you were to see this cross-section, that here's this is a really well-defined thing. This is the spinal nucleus of cranial nerve number 5. The next thing anterior and lateral to it has to be the posterior posterior spinocerebellar tract, and the next thing next to that is the anterior spinocerebellar tract. Those are headed up to the inferior cerebellar peduncle. They're headed up that back of the pons. They're going to end up going in that inferior cerebellar peduncle into the cerebellum is where they're going. Okay. And then we have L. This is the pyramidal decussation. This is where the pyramids. This is our pyramids right here. This is the decussation of those crossing. This is lateral cortical spinal tract right out here is M. This is the cortical spinal tract, and these are those fibers crossing at the decussation of the pyramids. All right, and then O, why am I not seeing O on here? Can you guys see O on? What's that? Oh boy, it's really, yeah, I knew it was right there.
More anterior.
Oh, I see it now. Yeah, thanks. Should have brought my glasses today. Yeah. So we're down low, it's in this region here. This is the spinal lemniscus. This is our spinothalamic tract that is now in the medulla, so it's called the spinal lemniscus. And it's still relatively anterolateral here in the low medulla. Remember in the spinal cord it's anterolateral system, spinothalamic tract. Now we're in the brainstem, medulla, spinal lemniscus, and you're going to watch this thing's going to move more posterior as it moves up the brainstem, and as we move up in cross sections, and eventually to get right up there with the medial lemniscus once we're up in the high medulla and midbrain. Okay, they're going to be right next to each other. So that is the spinal lemniscus. Now we're going to move our way up to this cross section, and this cross section is right through the level of the nucleus gracilis and nucleus cuneatus. You're going to see these very prominently as this next cross section. And this is where we have also the decussation of the medial lemniscus. Okay, so the first cross section was the decussation of the pyramids, where the pyramids cross, the lateral cortical spinal tract fibers. Now we're up in what's called the decussation of the medial lemniscus. This is where those medial lemniscal fibers, our dorsal column, medial lemniscals, are going to cross as they're going up. Okay. So here, let's look at these again. So here's this white area here, lighter color area. This is the nucleus gracilis, C. And then the darker area, just a wrapping kind of around it here. This is the fasciculus gracilis. And now here, E, this is the nucleus cuneatus. Now we see it really prominently. Before we were too low to really see it. Now we're really right in it. These nuclei extend up and down a little ways, but we're right in the heart of the nucleus gracilis and nucleus cuneatus. And then this is the tract, the fasciculus cuneatus is this whole real dark area around that. That's fasciculus gracilis, or cuneatus, D. F this is the spinal tract of cranial nerve number 5, and G is the spinal nucleus of cranial nerve number 5. So the tract here, and the nucleus there of the spinal nucleus. H and I, this is that posterior spinocerebellar tract. I is anterior spinocerebellar tract, kind of again right there in front of that spinal nucleus. Here's our pyramids. I should go back here real quick. I wasn't really clear. So here's our pyramids here. Our cortical spinal tract fibers, this is where the cortical spinal tract starts to originate. Your cortical spinal tract fibers are coming down the pyramids here from above, and then they're going backwards. They're going this way and crossing to go back. This is just the starting formation of your cortical spinal tract. So remember, those cortical spinal tract fibers come down the front of the cerebral peduncles, the front of the pons, the pyramids, and then they actually cross and dive backwards to become the lateral cortical spinal tract as they go down the spinal cord. So this is where you're just beginning to form your lateral cortical spinal tract, and they're going to move from the front here, and those fibers go back, and then in the spinal cord they're going to stay in that lateral part of the spinal cord as the cortical spinal tract. So I think I was almost showing them crossing this way. They're starting in the pyramids and then crossing back that direction. Sorry about that. So here's our pyramids here. So we're above now we're above where they're going to be crossing down lower to go back to. So we're not going to see any kind of lateral cortical spinal. We're not seeing any cortical spinal tract here. Where this is those fibers are in here in the pyramids right now. But we do start to see this medial lemniscal fibers and this starting to the crossing here of the decussation of the medial lemniscus. And so what's going to happen here is, remember, so these fibers are coming up from the dorsal columns and they're synapsing on cell bodies in the nucleus, gracilis, and cuneatus here, and then those are going those axons then are going to come over here, and they're going to wrap around here, and they're going to cross, and they're going to start forming the medial lemniscus. And so you have the same thing happening here. These fibers come over here, and they cross over to form the medial lemniscus. But this is the crossing point here. These fibers here, as they're kind of cruising around this way, these are the internal arcuate fibers. They're arcing around that center of the medulla there and then to cross at the lemniscal. This is the lemniscal decussation right in the center here. Okay, and then this is just the beginning of the medial lemniscus. Before then they start going up from there as the medial lemniscus. And then J is the spinal lemniscus. This is the pain and temperature pathway is right here. Posterior spinocerebellar, anterior spinocerebellar, spinal lemniscus. So it still hasn't started moving posterior yet. It's going to start doing that here real soon. But we're still in the medulla where the spinal lemniscus is still sitting in that anterolateral position, kind of as part of that anterolateral system. All right. Now we're up in this region here. We are at the level of the olives. We're at the mid-olivary level here is what this particular cross-section is defined as. So we get 3 cross-sections through the medulla. Fortunately, with the other ones, you only have 1 cross-section through each of the other ones. So the medulla is definitely the most challenging because it's longer and it has more stuff in it that we care about. So we're at the mid-olivary level. Notice that here we're starting to flare out right here. So you're going to see in the cross-section it flaring out, and this almost looks like a little bit of a butterfly look to it when we look at the cross-section. So you can see this flaring out happening right here, and that's because that's actually here, this flaring out starts to widen out here because this is your spinocerebellar tracts, which are now becoming your inferior cerebellar peduncles. So those are going to be the things that are flaring out here that we're seeing start to develop are your inferior cerebellar peduncles. They're going to go into your cerebellum here and the back part of that brain there. So a little bit longer list of things here. Let's just get through this and then we will let you go on break. C back here, this is just the bottom part of the 4th ventricle we're seeing back here. If we go through here, so we're seeing this little region right here, we're looking at the 4th ventricle. That little space there is the bottom of the 4th ventricle we're looking at. So we're looking right down on this little bottom of the 4th ventricle in that cross section. E, so this is the inferior cerebellar peduncle, right here and here. We no longer see the anterior and posterior spinocerebellar tracts because they've both entered in as now they've become the inferior cerebellar peduncle. So now they're gone because they're all together and going in the inferior cerebellar peduncle. F is here is the spinal tract and spinal nucleus of cranial nerve number 5. Spinal tract to be here, spinal nucleus is right there. So that's the spinal tract and nucleus. So cranial nerve number 5, we're still seeing that's that long descending nucleus, pain and temperature from the face, all the way through the medulla into the spinal cord. H, this is nucleus ambiguous. Okay, it plays some role for motor function. Remember, for the glossopharyngeal nerve, which is just the stylopharyngeus muscle, and then also for the vagus nerve, just some of the pharyngeal muscles. Okay, it's a motor nucleus, and you really can't. You'd have to have it marked on there, and this is the cross section you would see, and I would say, I would have it circled or highlighted, and I'd just say, what is that? You have to know that's a nucleus ambiguous. On these cross sections, I will actually circle the letter. So in the lab practical, I will actually have this thing, the edges and borders defined, and I'll say identify E. And I'll have those borders identified like that, so you hopefully can get that. So we did spinal lemniscus. Next one is spinal lemniscus, I. Spinal lemniscus is still sitting kind of very lateral right here. The olives are here now. We see the olives, but the spinal lemniscus is right here. But remember how everything, the spinal lemniscus, remember you had your anterior and posterior spinocerebellar tracts. Well, now they're not there. Now we've got the inferior cerebellar peduncle. But the spinal lemniscus is still sitting right near where those spinocerebellar pathways were, and now it's inferior cerebellar peduncle. But they're all M. This is the hypoglossal nucleus, and X right here. This is little nerve fibers. This is hypoglossal nerve fibers that are coming out right here. And this is the olive here, and this is this ventro-intermediate fissure right here where the hypoglossal nerve exits out of, between that olive and the pyramids. So that's the hypoglossal nucleus, M, and X is the hypoglossal nerve. N is the dorsal motor nucleus of cranial nerve number 10. Okay, so this is N is the dorsal motor nucleus of cranial nerve number 10. This is visceromotor. This is cranial nerve number 10, visceral drive to your parasympathetic control of your visceral function, dorsal motor nucleus of 10. P, right here, is the solitary nucleus. This is that cross section we showed you. Where we saw in that pontomedullary area where we're going to see a lot of these cranial nerves, nuclei. And so solitary nucleus, remember, it plays a role. It's a sensory nucleus. Taste and also visceral sensation goes to here. And remember, there's like 3 cranial nerves, 7, 9, and 10, that use this solitary nucleus for subserve different sensory functional roles as the solitary nucleus. Q out here is the medial vestibular nucleus. R is the inferior vestibular nucleus. Then S out here is the accessory cuneate nucleus. T, all of this out here, this is reticular formation. Reticular formation that we talked about, that we can divide into as longitudinal zones of midline, medial, lateral, reticular formation zones there. Why I don't have on here? Do I have it on here? The medial lemniscus on here? Where is that? Not why? Oh, L. I skipped over that. So this is the medial lemniscus, is this whole region here. Don't worry about V and W. They actually divide it up to upper and lower body parts. You don't need to know that. Just know this whole region here is the medial lemniscus on both sides. And then U right here, that's the medial longitudinal fasciculus, the MLF, is running right here, just off the ends of the medial lemniscus right now. Medial lemniscus is real medial right here. Then it's going to start twisting and flaring out, and then spinal lemniscus is going to go with it as well as we start moving up into the pons and up into the midbrain. Okay, but right now it's real medial, and it's going to start twisting and getting more this orientation. It's going to start twisting and getting more oriented like this, and then this guy, the spinal lemniscus, is going to move up out with it and get towards the end of it like that, and join up with it once we get up higher in the as we move up through the, remember the medial lemniscus is ribbon-like, and it kind of this ribbon twists as it goes up in your brainstem there. This area right here, you pretty much just have to memorize it and just go through and just kind of, there's no real good tricks for that. You're just going to have to like make sure you know what each of those guys are. O is a solitary tract. I don't have it listed on there, but that's what O is. There's a tract, because you have all these cranial nerves that are going to that solitary nucleus, and there's a lot of fibers going to that, and they actually form a little tract called the solitary tract of the axons that are going from your cranial nerve number 7, 9, and 10 that are taking sensory information to that solitary nucleus. So just in case you're wondering what that O is, that's a solitary tract. That's what O is. All right. I can feel the energy level getting higher in the room, that you guys are just really loving this, soaking it all in. So that means it's a good time for a break before you guys get too crazy and rowdy on me. I'm going to go out and relax a little bit. All right. Working our way up. We are in the pons. Only one cross section here. So big picture, pons, big picture. Functions. Processes motor information from the cortex. Hey guys, calm down. I know you guys got excited out there. You really did. Processes motor information from the cortex and feeds it to the cerebellum. So in the pons, this is where those cortical pontine fibers come down, and then synapse, and then go to the opposite side of the cerebellum. That's what we mean here, is that there's a copy delivered to the cerebellum. Pontine cranial nerve nuclei are where we get some sensory information from the face. There is some pontine cranial nerve nuclei for cranial nerve number 5, trigeminal nerve, that are in the pons. Okay. The control for muscles of facial expression, cranial nerve number 7. The nucleus for cranial nerve number 7 is in the pons. And the abducens for lateral movement of the eye, cranial nerve number 6. And then also cranial nerve number 5, motor, for chewing. Okay, muscles of mastication. These are things that are motor and sensory functions of the pons that are more clinically relevant to you. So this is the level that we're going to be looking at this cross section. So it's right through almost the mid-pons. The mid-pons cross section, we're just maybe catching a little edges of the superior cerebellar peduncle coming up here, and here's the middle cerebellar peduncle. This would mainly be considered more superior cerebellar peduncle that we're cutting through here, coming up this way. So that's what we're seeing here. Here's the little top of the fourth ventricle. Looking back here, this is actually a little covering right here. This is called the medullary velum right here. Superior, no, this is the medullary velum's down here. I forget what this one's called. Superior medullary velum or something. But anyway, if we cut that little thing out, this is where that rhomboid fossa would be. And we're seeing that little tiny tip here. There's a little space there. It's still the fourth ventricle. So that's what B is, a little fourth ventricle. Right before it goes in here, becomes a cerebral aqueduct in the midbrain. Okay, so that's what we're seeing there. D, there's a little nucleus right here. D, this lighter color area, that's the mesencephalic nucleus of cranial nerve number 5. However, we're just seeing the bottom edge of it. We're not quite in the mesencephalon. We're in the pons here, but we're really close to where this is where the midbrain kind of starts right here. So we're seeing a little bit of this mesencephalic nucleus, which is one of the cranial nerve 5 nucleus that is just for processing the TMJ sensation. If you remember that one, has the TMJ sensation goes to the mesencephalic nucleus for the trigeminal nerve. That's what you're seeing there is D is the mesencephalic nucleus of cranial nerve number 5. E, this is the MLF, the medial longitudinal fasciculus, okay, is E. It's joining up those cranial nerves of the oculomotor, abducens, trochlear nerve nuclei with the vestibular nuclei that go down to the medial activating pathways, vestibulospinal, reticulospinal tracts. That's the MLF. That's right there. H is the superior cerebellar peduncles. Okay, that's what I showed you back here. Is this little area right here we're cutting through is the superior cerebellar peduncle. E is MLF. Okay, we got that. H. K. Here's the spinal lemniscus. Now it's moved. It stays lateral the whole time, but it's moved back. You know, here's the pons, basilar pons is this whole area out here in front. And then this right here is the medial lemniscus, L and M together. L and M are just showing you this differentiation between upper and lower body arrangements there, but don't worry about that. Just know that this is the medial lemniscus as a group here. And O, there's a little region right here which is called the trigeminal lemniscus. That is your pain and temperature from your face and head. Remember, so pain and temperature, it goes in to your trigeminal nerve, it actually goes down via the spinal tract of cranial nerve number 5, and then makes connections with the spinal nucleus of cranial nerve number 5 in the medulla and all the way down into the upper spinal cord. Then it crosses over and ascends on the opposite side as the trigeminal lemniscus. And eventually the trigeminal lemniscus gets close to and hooks up with the medial lemniscus and the spinal lemniscus. So once we get into this pons area, mid-pons, all of our sensory pathways for our face and body, proprioceptive, pain and temperature, all right next to each other. They all converge in that area. So remember, down lower, our medial lemniscus was down in medial, you know. And then remember I said it starts to rotate and kind of starts to twist and then move back this way. And then our spinal lemniscus was usually out here, and now it's kind of just joining up as these pathways move up and can converge on each other and get near each other once we get up into this mid-pons region. And then this whole basilar pons, this big basilar pons, what's running down the front of that is you have your pyramidal tract fibers, cortical, spinal, and cortical pontine fibers are all running down the front here, and those are all the dark stained stuff is axons. All the dark stuff is the axons, okay? And those are cortical spinal tract fibers, cortical bulbar fibers, cortical, you know, they're just a mix of fibers that are running down through the front part of the pons. Some of them stop in the pons, the cortical pontine fibers, and they synapse on the lighter colored areas here are pontine nuclei. So all the lighter areas are pontine nuclei. So again, some of these fibers run all the way down through the pons as cortical spinal tract / pyramidal fibers that go into the pyramids. Some stop at the cranial nerves, and then some will stop and synapse on a pontine nuclei that then this pontine nucleus crosses over, and it's going to go down a little lower. It's going to go through the middle cerebral peduncle and go into the other side, opposite side of the cerebellum, carrying a copy of motor information to the cerebellum. nearly as much stuff on that cross section. And then kind of the same in the midbrain. The midbrain's not too bad. What does the midbrain do? Eye movement, cranial nerve number 3. The oculomotor nucleus is in there. As far as and also the Edinger-Westphal nucleus, the parasympathetic component of the oculomotor nucleus. It's a relay center for reflexive eye and head movements associated with both visual and auditory information via the tectum, the superior and inferior colliculi. The pupillary reflexes, consensual and accommodation reflexes are mediated at the level of the midbrain. Our substantia nigra is there that projects up to the basal ganglia circuitry. Some upper extremity movements bias upper extremity flexion via the rubrospinal. The red nucleus is there. Rubrospinal tract starts there. Locomotion of postural influence via the pedunculopontine nucleus. The pedunculopontine nucleus is there. And then also pain suppression. There's an area around the cerebral aqueduct called the periaqueductal gray, the PAG, or the PAG. The PAG is where we have those midline reticular formation areas in the periaqueductal gray that project down tracts to the dorsal horn of the spinal cord and helps with pain suppression. Although some of the periaqueductal gray tracts go down to the raphe nuclei and help the raphe nuclei do their job. So the periaqueductal gray tracts don't actually go all the way down to the dorsal horns. They help to tell the raphe nuclei to do their job even better. And the raphe spinal tracts go down and project down to the dorsal horn. So here we are. This is the cross section. Really pretty much a midbrain, which just happens to be right through the superior colliculi. They were at the level of the superior colliculus here. So it's going to look a little bit like this. Pretty characteristic here of seeing the red nuclei. These are really obvious, the red nucleus on each side here. These bumps back here, this is at the level of the superior colliculus. So this is the superior colliculus sitting off the back here. Don't need to worry about this too much, but this for some reason it got cut off here, but that's the medial geniculate nucleus, medial geniculate body or nucleus. That's a relay for reflexive movements, or for actually that's the area where auditory information goes before it goes to the cortex, is the medial geniculate nucleus. The lateral geniculate nucleus is where it goes. These are bumps off the thalamus. The medial and lateral geniculate nuclei are off the kind of back of the thalamus. The lateral geniculate body or nucleus is for relay for vision. The medial geniculate body for hearing. Okay, that's going to go to the cortex. D, all this area in here, this is all reticular formation in the midbrain. E is the spinal lemniscus. F and G together, this is your medial lemniscus. So this medial lemniscus, down low, when it started, it was oriented anterior to posterior. As it works its way up, it starts to get more this way, and it continues to more this way. Now it's more oriented almost anterior to posterior once you get up in the midbrain. So it's just doing that twisting thing as it goes up the brainstem. So now and then that spinal lemniscus still stays tacked on here to the tip of that medial lemniscus. So that's that pain and temp from the body, proprioceptive. Then I is the trigeminal lemniscus. The trigeminal lemniscus is sitting right there. So they're all real close to each other because they're going to eventually go up into the internal capsule. They're going to go into that posterior limb of the internal capsule really close to each other to head up to the cortex. Well, they're going to go to the thalamus, stop to the thalamus first, and then go internal capsule. H and T, or H and T, is this whole region here. This really light colored area, that's the substantia nigra, because there's cell bodies there, so they don't stain. Remember that. So this is a big nucleus essentially. So this is the substantia nigra, is that area there. K, we already showed you the red nucleus. N, this is the cerebral aqueduct. O, this whole area kind of around the cerebral aqueduct. This is all periaqueductal gray matter, the PAG, P-A-G, periaqueductal gray. P, little nucleus on each side here, that's the Edinger-Westphal nucleus. The parasympathetic preganglionic fibers are going to go for contracting your pupil for pupillary constriction, and also to the muscle of your eye to help lift your eyelid up a little bit. That's the Edinger-Westphal. Q, right here, this is the oculomotor nucleus on each side. That's going to all the extraocular muscles, except for superior oblique and abducens. It's going to rectus muscles and inferior oblique for motor eye muscles. Okay? R is the MLF right here. This is really where the MLF starts or ends in a way. The MLF starts and joins up the oculomotor nucleus, and then it projects down and joins up the trochlear nucleus, the abducens nucleus, vestibular nuclei, to the spinal cord, down to the vestibular and reticulospinal tracts. That's the beginning. This is really kind of the beginning of the MLF. And it's still, the MLF stays almost in that same region the whole way down. It's kind of in that medial, slightly posterior, very middle origin as it runs down through the brainstem. And then S, these little guys right here, oculomotor nerve fibers that are running out. This is that interpeduncular fossa right here. And then this area here, Z, or all these together, this is your crus cerebri. Crus cerebri, if we look at it in this, I don't know why I don't have it listed on there. They definitely need to know that. So Z, crus cerebri. If you're looking at it from the front, we call it the cerebral peduncle from the outside, but in cross section it's called the crus cerebri. This is just dividing that up into like upper, lower thoracic fibers, because there's some somatotopic arrangement there. You don't have to know those. Just know that this is the crus cerebri. Those are motor fibers running down the front of the midbrain to level the superior colliculus. Got all those? You will in 2 weeks. Now let's talk about disorders, damage to the brainstem, and what that leads to. And understanding those cross sections, it helps you know what's happening here. Typically, if somebody has brainstem dysfunction, not always, but most commonly, they're going to have one of these that helps give some of that away, that you're looking at some lesion in the brainstem. Dysphagia, which is difficulty with swallowing. Okay, swallowing disorder, tongue movement, soft palate movement. Something is impaired there, but they have trouble with swallowing. Diplopia, double vision of some type. Any kind of damage to the MLF or one of the oculomotor nerve, trochlear, abducens nucleus means that one of your eyes isn't going to work and they're not going to sync up with the other eye. And that typically always leads initially to double vision. Your brain can do some correcting over time, but when you first have damage to one of those cranial nerve nuclei, it's very common to have double vision because you just can't get the eyes to totally sync up and work together. Dysmetria, some form of ataxia. I would say dysmetria / ataxia. If you impact any of the connections going into or out of the cerebellum, cerebellar peduncles, any of those pathways coming into the cerebellum or out of the cerebellum can cause incoordination in an ataxic type way. Dysmetric ataxia. And dysarthria would be difficulty with speech. Not the planning part of speech, but the actual production of speech where the voice sounds slurred or wispy. They can't, can't close their mouth all the way. But you can tell they know what the words they want to say, and they can put the words together into sentences. But they just have difficulty producing the speech because of weakness of those muscles of the face, typically, which involves any of the cranial nerve nuclei that are involved with your, larynx and pharynx, and so cranial nerve number 9, 10, tongue, hypoglossal nerve, um, or facial nerve. Any of those cranial nerve nuclei could cause this dysarthria. Okay. Other common manifestations of brainstem dysfunction: problems with regulating vital functions, particularly respiratory and cardiac rates and so forth. So people that have brainstem dysfunction can have irregular respiratory and heart function kind of things going on. Hey, Dennis. Disorders of consciousness. If you affect any of that reticular formation and that reticular activating system that helps you stay awake and alert and produces norepinephrine and all that kind of stuff, and dopamine and right balance of that, you can have trouble with consciousness. Okay. Also, another common manifestation of brainstem is where you have a combination of ipsilateral and contralateral signs. So it means that you may have a lesion in the brainstem on the right, and you might have right-sided facial weakness or sensory problems, but left-sided body problems. Anytime you have this, opposite, where one side of the face and the opposite side of the body are having dysfunction, that generally may be an indicator that there's something in the brainstem going on. Versus if it's the whole side of your face and body all on the same side that are being involved, sensory or motor, you're above the brainstem typically, okay, into the cerebrum.
Is that like that patient that the prison guard thought he was faking it, and you were like, no?
You do get some of those with spinal cord lesions. So he had a spinal cord, that's the Brown-Séquard lesion, where you could get. That's the only other thing that will give you some mixed ipsilateral, contralateral signs. If you damage half the spinal cord, where you get loss of proprioception on one side and loss of pain and temperature on the other, this would be not so much of loss of individual modalities, it's loss of some type of function on one side of the face versus the other side of the body. So that's a good distinction to kind of understand, is that we're talking about one side of the face versus the other side of the body. Then that helps you locate it to the brain, to the brain stem. So we're going to go through. There's some common specific brainstem syndromes or lesions. These are the ones that are most common. They typically are associated with the vascular territory. The most common cause of neurologic disorders is strokes. Just like heart attacks are the most common cause of death, and cardiac, it's blockages of arteries and circulation to an area, and these are the most common syndromes you're going to see associated with that. So the first one is actually a more rare to see this, but does happen. It's called the medial medullary syndrome. So medial area, the medial portion of the medulla is involved. Okay, and it typically happens just on one side versus both sides, and it typically happens because a branch of the anterior spinal artery is damaged. Okay, so the anterior spinal artery runs all the way down the front of your spinal cord, but it also extends up and runs down the front part of your medulla too. And we'll see the origin of the anterior spinal artery next week, where it starts and where it comes down the front part of your brainstem. So if you have damage to it, then it runs right down the middle of your brainstem here, and there's branches that project off of that. So if you block the anterior spinal artery, or as it branches off there, you can cause problems with this region of your medulla. And so the things you're going to have, the deficits associated with this particular, and this is where you have to kind of recognize these clusters, and then it's like, and be able to recognize on a problem or a case to say, this cluster of symptoms, that fits this medial medullary syndrome. If you know what is in the medial part of the medulla, that you can maybe reason some of that out. And so, first of all, you get damage to the pyramid, right, on one side. If you have damage to the pyramid on one side in this medial medullary system, you're going to get contralateral hemiplegia. So we're talking about relative to where the lesion is. So in this case, the lesion is on the left, because this is anterior, this is front. And so the lesion is on the left side, left pyramid, and so you have cortical spinal tract fibers, pyramidal fibers running down the front here. They're going down lower before they cross over, right? So they're going to cross down, the decussation of the pyramid's lower, and you've damaged these cortical spinal tract fibers, so they're going to have weakness on the opposite side. The lesion's on the left, they're going to have right-sided hemiplegia. They could have right-sided hemiplegia in this case. They're going to have contralateral loss of position sense. This together, this is that L region, this is the medial lemniscus. So they've damaged the medial lemniscus. And the medial lemniscus is already crossed down lower here. This is where this lesion typically happens, above where the dorsal columns have come up, and they've crossed over in the decussation of the medial lemniscus, which is just a little lower. It's a little bit lower down on the medulla, and it's most of these fibers have all crossed over by this point. And so again, you're going to lose the right side. If this is a left-sided lesion in this particular location, you're going to get contralateral loss of position sense. And then you're going to get ipsilateral deviation of the tongue. And so here's the hypoglossal nerve nucleus. The nucleus and the nerve runs through this area, and so you're damaging the nerve fibers as they go to try to exit out that ventro-intermediate fissure there. And so these are going to your left side of your tongue, right? And so what's going to happen is your left side of your tongue is weak, and so your right side of your tongue stronger. It's going to, when you try to stick your tongue out, the right-sided muscles are going to make your tongue push and go to the left, which is the same side as the lesion. So it's an ipsilateral deviation of the tongue. The tongue's going to drift to the left because the right-sided muscles are pushing out, and there's nothing to oppose it on the left, so it's going to tend to bend the tongue to the left as it goes out. So those are the main things. It's not going to affect pain and temperature because here's the spinal lemniscus right here. I is the spinal lemniscus. So pain and temperature is making it past that lesion just fine. It's not affecting any of the cerebellar peduncles or spinal cerebellar tracts over here, so they don't have any ataxia. All these other cranial nerve nuclei and vestibular nuclei are just fine. So it's very kind of unique, and it has just these features to it that would be indicative of a medial medullary syndrome. Now, this is the most common one here, is what's called lateral medullary syndrome, also known as Wallenberg syndrome. Okay, this is much more common. This is because of damage to a branch of the posterior inferior cerebellar artery. And you'll see that in next week, the origin of the posterior inferior cerebellar artery. There's a branch of that goes back to this back part of the medulla and supplies this posterolateral portion of the medulla. Okay. Deficits, what are you going to have? You're going to have contralateral loss of pain and temperature from the body because of damage here to the spinothalamic tract. That's that I right there. Spinothalamic tract is damaged. Remember, that information all came in way down low in your spinal cord and crossed over already, right? So that information came in down low, crossed over, is coming up as the spinothalamic tract. So you're going to have loss of pain and temperature, the opposite side of the lesion, contralateral loss. So this is a lesion on the right. This is a right-sided lesion. We have left-sided pain and temperature loss in this case. We're going to have ipsilateral loss of pain and temperature from the face because of damage to the spinal tract and nucleus of cranial nerve number 5. So this is the spinal tract and nucleus right here of cranial nerve number 5. So remember, that information, pain and temperature from the face, comes in above this, and it goes down to make these connections in the spinal tract of cranial nerve number 5. And you're impacting and damaging this as it tries to come in from this side before it has a chance to cross over and come up as the trigeminal lemniscus. So you're blocking the information of pain and temperature coming in from the right side of the face. That's why it's ipsilateral to the lesion. The lesion's on the right, the loss of pain and temperature for the face is on the right. But it's contralateral for the body because it's already crossed over in the spinal cord. So that's an indication we're in the brainstem. You've got loss of body sensation on the left, the loss of some facial sensation on the right. So that's a good indication that we've got a brainstem lesion here going on. You might get some dysphagia. hoarseness, decreased gag reflex, because you've impacted nucleus ambiguus, okay? Cranial nerve number 10, which is this H right here, nucleus ambiguus. That's the motor function of your soft palate, your larynx and pharynx, so they're going to have some swallowing difficulty impacting that, okay? They may have dizziness and nausea because of damage to some of the vestibular nuclei, okay? So you've damaged some of the vestibular nuclei here and can cause them to feel some vertigo. And when you have vertigo, you often feel nauseous too, especially initially, and actually it can happen all the time. So they'll experience, because you've damaged some connections with the vestibular nuclei, they can experience some vestibular dysfunction. This would be a central vestibular dysfunction, not a peripheral vestibular dysfunction, okay? They can have ipsilateral ataxia because you've damaged some of the spinocerebellar fibers. In this case, you've damaged the inferior spinocerebellar tract. The inferior spinocerebellar, inferior cerebellar peduncle. Sorry. So this is the spinocerebellar tracts coming together to deliver it up to the cerebellum. And remember, the connections of the cerebellum are ipsilateral. So if you damage the left cerebellum or any of its connections on the left, you're going to have ataxia on the left. Okay, and so ipsilateral ataxia, right-sided lesion, right-sided ataxia. The other thing you're going to see is this thing called Horner syndrome, ipsilateral Horner syndrome, because you've damaged the descending sympathetic pathway that goes to the sympathetic neurons called the DLF, the dorsal longitudinal fasciculus. You cannot see a distinct dorsal longitudinal fasciculus. It's somewhere in this region, kind of in here. There's fibers that are running. They're a little more spread out, so it's not like you see this distinct tract. So the dorsal longitudinal fasciculus runs through this region, and if you impact that, you can get this cluster of symptoms of impacting sympathetic control to your body, but you tend to notice them most in the face and head. We'll show you here what those symptoms look like. So if you remember, here's your hypothalamus, and this is the dorsal longitudinal fasciculus, and it runs all the way down your spinal cord, but it's running through your brainstem. And so if we're here, here's our pons, here's our medulla. So if we're impacting this thing anywhere in the pons or medulla, if you impact the DLF, and medullary syndrome, this lateral medullary syndrome, Wallenberg's, happens to impact the MLF because it tends to be a little more posterior lateral, and it goes down to help facilitate sympathetic outflow from the sympathetic neurons down in your spinal cord. And if you remember, some of those first few sympathetic T1, T2, they project back up to the ganglion in your cervical spine and project up to the eye and face, and to supply sympathetic control to your face and eye, eyelid, sweat glands to your face, pupillary dilation, okay? So if you damage the DLF that helps to facilitate that, you can get an impairment in sympathetic control to your face, but also some to the body as well. You just tend to, the symptoms are more obvious in the face because you actually see impairment. You see a pupil that's is constricted now, and you see an eyelid that's drooping now, and you see maybe some changes to how the oil and sweat on the face type thing, where you have less of that going on. So this is what Horner syndrome looks like when you're looking at somebody. So you notice that the eyelid is slightly droopy because we do have a little bit of sympathetic. We have parasympathetic and sympathetic control to that upper eyelid that helps lift it up. You have to have both of those working to have normal. And so if you lose either the parasympathetic or some of the sympathetic, your eyelid will droop some. So we get the eyelid drooping. You'll notice that this pupil is more constricted because we've lost some of the sympathetic outflow or control to that pupil, which this sympathetic system dilates. So now it's purely parasympathetic from that Edinger-Westphal nucleus, is keeping it overly constricted because it's not being balanced by the sympathetic nervous system. Animals can even get Horner syndrome. This is in a dog. You know, of course, their eyelid goes up in a dog when they blink and so forth. So this is their drooping eyelid. It's drooping. It's not drooping down. It's drooping that way because they've lost some of the sympathetic tone or control over the eyelid. And then if you were to pull that down, this pupil is pretty big and this pupil is smaller. So this is actually a Horner syndrome, can be seen in animals as well. They have a dorsal longitudinal fasciculus that goes to supply that. So that was lateral medullary syndrome, Wallenberg syndrome. Okay. Now we're in what's called the pons. We're in the pons, and this is called medial pontine syndrome. So it's the middle part of the pons, that medial aspect of the pons. And this happens to be when you have damage to what's called the paramedian branches of the basilar artery. So the basilar artery runs right down the front of your pons in the basilar groove, and there's these large branches called paramedian branches that go and dive into the deep pons to supply this whole medial zone of the pons on each side. So if you get some blockage of these paramedian branches, you can have this medial pontine syndrome. Again, just kind of understanding the cluster of symptoms will give away what's happening. So, first symptom, contralateral hemiplegia. You've damaged a pretty good chunk of the basilar pons, and there are pyramidal tract, cortical spinal tract fibers running down the front of that. They're going down to the medulla to cross over to the other side, down below. So if you damage, this is a left-sided lesion, you're going to have you could have right hemiplegia. You could have right spastic hemiparetic weakness. This is upper motor neuron problem damaging the pathway. You could also have contralateral loss of position sense and vibration because you've damaged the medial lemniscus. Here's the medial lemniscus here. This is in the pons where it's still sitting in this medial lateral kind of orientation, but with this medial pontine syndrome, you get most of the medial lemniscus on one side. And if you remember, so these have already crossed over down lower. These crossed in the medulla. They were coming up, crossed the medulla. So when you block them here, this is right-sided. You're going to have left-sided contralateral loss of proprioception, conscious proprioception. You are also going to have ipsilateral lateral rectus paralysis. So the abducens nerve and nucleus, okay, can be impacted, which is F, which is actually this. It's this structure right here. Here's F right here. Here's the abducens nucleus, and this is the nerve that comes out, and it's diving down. Remember, it's up higher in the pons, and it dives down, and comes out that pontomedullary junction. So it's diving down through the pons, and a medial pontine syndrome like this can impact the abducens nerve as it's on its way through the pons to go out down below and that could cause ipsilateral lateral rectus muscle weakness. Okay, so that eye, if you've got that ipsilateral lateral rectus muscle, your eye will be sitting more medial on that side. Okay, and you'll have double vision likely with this as well. You can also have difficulty or paralysis of conjugate gaze especially towards the side of the lesion. And so remember, conjugate gaze is your eyes moving together, which our eyes typically always move together conjugately. They move the same way. You use the MLF so that when one eye is moving one way, it can tell the other eye to move the opposite. Okay, and so if you damage the MLF on one side, and this is the MLF is back here. It's those two little areas right back there, right near the fourth ventricle here. But there's the MLF. If you damage the MLF on one side, they have difficulty with conjugate gaze, moving their eyes together to the same side as the lesion because of damage to the MLF. So they'll just kind of get to like midline, and they can't go past midline with the MLF not working properly, that you can get your eyes to work together to cross midline. That's the medial pontine syndrome. And then let's do lateral pontine syndrome, then we're done. Well, for today. So here's now, we're in the same cross section of the pons here. This is the basilar pons. This is actually the dentate nucleus. This is the cerebellum back here is what you're seeing back here. Just don't let that freak you out or distract you. Deficits, ataxia, unsteady. They fall towards the side of the lesion. We're damaging, this is the middle cerebellar peduncle in here, so we're damaging some of the cerebellar fibers that are trying to cross over and tell your body what's going on with motor system, and you're damaging cerebellum and the connections to the cerebellum. Anytime you damage any of the cerebellar peduncles, you're going to get ataxia on the same side. So we're impacting this one of the cerebellar peduncles. That's all you really need to know there. That's going to cause ipsilateral ataxia, and they tend to drift and fall to that side too for some reason because of that. They may have vertigo, nausea, and deafness because you've also impacted potentially some of the vestibular and cochlear nerves in the nucleus. Okay? Let's sit over in that area. This is like G is the lateral vestibular nucleus. You don't have to know that on this cross section. These pictures won't show up on the exam. It'll be those other stained ones that you would see, but the vestibular nucleus is over here, but also the connections with the cerebellum, right? You have the floccular nodular lobe that connects directly with vestibular nuclei. If you damage any of those connections with the cerebellum or the vestibular nuclei, you're going to get some vertigo, dizziness, and this one could potentially cause some loss of hearing because the cochlear nerve nuclei are in that same region as well. They don't have a picture on here of that, but you could damage, because these lesions aren't just this little tiny. They're not only in that section, but they're going up and down a little bit too. They extend up and extend down a little bit. Ipsilateral facial muscle weakness, paralysis. This is actually right here. This is the facial nerve nucleus right here. On this side they're showing, and the facial nerve is kind of interesting. It actually, the axons project, they wrap around the abducens nucleus before they exit out as the facial nerve. Down at that pontomedullary junction again, down lower, they then also descend down. So you can impact the facial nerve on that same side. So this is a right-sided lesion, you're going to get right facial nerve weakness, so ipsilateral to the lesion weakness. Ipsilateral paralysis of muscles of mastication, because you can affect the trigeminal motor nucleus in this region too. The trigeminal motor nucleus tends to sit in this pons area. This origin of your trigeminal nerve also comes out in that region. Okay. Ipsilateral Horner syndrome, same thing we saw in Wallenberg syndrome, ipsilateral Horner syndrome, because that DLF is kind of running probably somewhere in this region here, the DLF, somewhere in this general region, the DLF is running down, some fibers of it are running down that region. Ipsilateral loss of pain and temperature from the face, because we can impact this I and H together. This is the beginnings of that spinal tract of cranial nerve number 5. We're just below where the cranial nerve number 5 comes in here. And so those fibers come in, they're descending down that track. So we're going to get ipsilateral loss of pain and temperature of the face, same side, because they're coming in that side to come down and then make connections with that spinal nucleus. Contralateral loss of pain and temperature from the body, because we're impacting the spinal lemniscus, which they show it here, and it sits here on this side. The spinal lemniscus is here and here. So we do impact spinal lemniscus, but all that information is crossed over from lower down the spinal cord and coming up this side of the body. So it's the opposite, contralateral loss of pain and temperature from the body. And we will also, here's that MLF, Q, MLF. Now we're affecting the MLF again, and that's again going to make it hard for conjugate gaze, especially towards the side of the lesion. And so in this case, it's a right-sided lesion, so they have trouble with conjugate gaze towards the right. Moving those eyes together is going to be hard for them to do with that MLF being affected. And this is because of long circumferential branches of the basilar artery. And so when we get to the circulation, here's the basilar artery sitting here. We have these short penetrating, these medial branches that come and supply this medial part of the pons, but then we have these lateral long circumferential ones that come around to supply this lateral portion. If those get damaged, that's going to cause this lateral pontine syndrome. We're going to stop there, give you at least 10 minutes to recover from that, or